All right, everyone, welcome to this first video for Unit 3, where we're going to learn about the electron and how it orbits around the nucleus. Now, what I want to say is back in middle school, you maybe learned that the electron goes around the nucleus, and it goes around the nucleus on specific energy levels. So there's specific energy levels in which it can exist, and you probably imagine it as a particle moving around like this. But the reality is that the electron doesn't necessarily act like a particle in the way that we normally think. It doesn't just orbit, kind of like the moon orbiting the Earth. It doesn't orbit in that way. It actually orbits or exists around the nucleus as a wave. And so because it acts like a wave, and we're going to talk about that here in this video, it's going to create different orbitals in which it can exist in. And so there's specific orbitals in which the electron can exist in, and by the end of this video we're going to learn those different orbitals. So let's go ahead and talk about the electron cloud. Now, the electron cloud consists of a very complex arrangement of orbitals within a series of main energy levels and energy sublevels. And so let's go ahead and break this down a little bit. If you remember, there's specific energy levels that an electron can exist in. And so we have the first energy level, which can have 2 electrons. We have the second energy level, which can have 8. And so those are main energy levels. Now, within those levels, there are sublevels that the electrons can exist in as well. And so those sublevels are going to be different, and that's what we're going to talk about here in a moment. So again, if you remember, we have the first energy level, which can have 2 electrons, the second, which can have 8. Maybe in middle school you learned that the third can have 8, but we're going to learn it's actually 18, and so on. And then within each level, there's sublevels that the electrons can exist in. So Erwin Schrodinger came up with these equations that describe the shape of these different orbitals that exist within these sublevels. And the way he came up with these equations is, at some point in time, we learned that the electron actually doesn't behave just like a particle, but it also behaves like a wave. And so you can think of like a wave in the ocean, and the way that a wave in the ocean behaves, some of the characteristics of that wave are how electrons behave as well. So it doesn't just orbit as a particle around the nucleus, but it acts like a wave where it comes in and out of existence in different points. Now, again, these equations that Schrodinger came up with are very, very complex. They describe the shape of the orbitals that these electrons exist in. And so let's talk about what an orbital is. Now, an orbital is a 3-dimensional region where you can probably find an electron. And again, it's going to be where it's going to be where an electron is most likely going to be found around the nucleus. And it's important to keep in mind that any orbital can have a maximum of 2 electrons. So as we're learning these different types of orbitals, particularly s orbitals, p orbitals, d orbitals, each orbital is going to have a maximum of 2 electrons. And we're going to use this fact, or this piece of information, later on in the unit as well. So let's first talk about main energy levels. So main energy levels will indicate the general amount of energy that an electron has, and it's really telling us how far from the nucleus that the electron is. And so the first energy level is closest to the nucleus, and it's going to have the lowest amount of energy. But when we go up to the second energy level, it's going to be a little bit farther. It's going to have a little bit more energy. It's kind of like the idea of potential energy or gravitational potential energy. If I have my mouse right here and I were to lift it up, it's going to have more gravitational potential energy. Same thing is true with an electron. If you move an electron up to a higher energy level, it's going to have more energy associated with it. So let's go ahead and take a look at this chart right here, because I think that this is going to be something that's very important to help us understand what's going on. If you take a look at the first energy level at the very bottom, you can see that as we go up to the second energy level, you'll see that the amount of energy increases quite a bit. It increases a lot. And in fact, when you go from the second energy level to the third, it also increases a lot, but notice how it's closer together. And when I say closer together, it's closer together in terms of energy. So what I really want to point out is notice how each time we jump up to a new energy level, it does increase in energy, but the amount it increases is not as much. And so that's something that we want to keep in mind for later on as well. So each row or period on the periodic table indicates an energy level. And so again, when we look at the periodic table, every single row represents one energy level. And it is important to note that as we move farther from the nucleus, the energy levels get closer together, kind of like what I was talking about in that graph 2 slides ago. And so the difference in energy is smaller. Now, what I want to really clarify is, as we go up in energy, the energy levels do get closer together, and the increase in energy is not as much, but it's still increasing in energy. So the fifth energy level is going to have more energy than the fourth, it's not going to be as big of a jump. Now, if you take a look here on the periodic table, again, each row represents an energy level. So I want you to take a look at helium in the upper right corner. It's in the first row, so that means it's going to have electrons that are in the first energy level. Go ahead and go down, go to neon, which is right below helium. You'll see it's in the second row, so that means it's going to have electrons in the first row and the second row, or in the first energy level and the second energy level. And then if you go down to let's say xenon down here, you'll see that it's in the fifth row, so that means it will have electrons that are in the fifth energy level. But it also will have electrons in the first, the second, the third, and the fourth energy level. And so you can see, depending on what row an element is, it'll tell you how many energy levels it will have electrons in. Now, energy sublevels indicate the different shapes of orbitals that exist in a particular energy level. And so let's take, for example, the second energy level. The second energy level has two types of sublevels, and we're going to talk about those sublevels here. So again, these sublevels are within the same energy level, however, they're different types of orbitals, and they actually do have different energies as well. We indicate these different shapes with letters. And so let's go ahead and talk about the first type of orbital, which is the s orbital. The s orbitals have a spherical shape, and there is one s orbital for any given energy level. Now, what I want to say is there's one s orbital for any given energy level, but remember a few slides ago, how many electrons can go into an orbital? 2 electrons can go into one orbital. So that means there's 2 electrons that can go in total in the s orbitals. And it'll make more sense when we get to the p orbitals, I think. But anyways, because there's only one s orbital and there's 2 electrons per orbital, that means there's 2 electrons that can go in the s orbitals. And this is the shape of the s orbitals. They are a sphere. It's amazing. All right, so if you take a look here, those 2 columns on the periodic table represent the s orbitals. And so, again, there's one orbital with 2 electrons, and notice how there's 2 columns. Now, something I want to point out is notice how helium is actually a part of the s orbital block, and so we call it the s block. And if you take helium and you move it all the way over, you'll see that it actually fits on that side. And so helium does have s orbital electrons. So, all right, the next type of orbital are p orbitals. All right, and so p orbitals resemble dumbbells. And so again, s orbitals were spherical, p orbitals resemble dumbbells or peanuts. They look like peanuts as well. And there are a maximum of 3 p orbitals in a given energy level. So let's think about this. There's 3 p orbitals in a given energy level. And again, there's 2 electrons per orbital. So if there's 2 electrons per orbital, and we have 3 orbitals, how many total electrons can go in the p orbitals? The answer is 6. Because again, there's 3 orbitals, 2 electrons per orbital, so there's a total of 6 electrons that can go in the p orbitals. And so let's go ahead and take a look here. These are the 3 different orbitals that the p orbitals have, and again, they look like dumbbells or peanuts or whatever you want. But the p block is going to be the last 6 columns on the periodic table. And so notice how those are 6 columns, because there's 6 electrons that can go in the p block. The s block had 2 electrons that can go in, and so that's why we have 2 columns. Amazing how the periodic table works out that way. So let's go ahead and move on here. But again, I want to highlight there's 3 orbitals in the p orbitals. Each orbital has 2 electrons, which is a total of 6 electrons that can go in the p orbitals in any given energy level. All right, now we have the d orbitals. The d orbitals often resemble clovers, and there are 5 d orbitals in any given main energy level. So let's go ahead and recap real quick. S orbitals have 1, p orbitals have 3, and d orbitals have 5. You see how it goes 1, 3, 5, and we have the f orbitals to talk about. You want to take a guess how many they have? They will have 7. But the d orbitals have 5 orbitals. 2 electrons can go into 1 orbital. So again, 2 electrons in 1 orbital. There's 5 orbitals. That's a total of 10 electrons can go in the d orbitals. And so if you take a look, these are what the d orbitals look like. You can see they're getting more complex. And so as we go in order of talking about these different orbitals, they start to get more and more complex. And something we want to keep in mind, and this is going to matter later on, is the more complex the orbital, the higher the energy is. So anyways, so the D block is this middle section here is where the transition metals are. And so you can see there's a total of 10 columns in the D block because there's 5 orbitals, 2 electrons per orbital for a total of 10 electrons, which gives us 10 columns. And so amazing how that works out. It's cool how the periodic table's, ordered in that way. So anyways, orbitals with higher energies than D's are particularly the F orbitals. They start to get really complex and it's difficult to represent what those orbitals look like. But the F orbitals are the next one. And then there are these theoretical orbitals called G orbitals. And so again, those are difficult to represent. But here is an image of what the F orbitals might look like, and they look pretty funky. And so that's kind of how I remember that, because F orbitals look pretty funky and they're very complex. And so again, there's going to be 7 orbitals in the F block, 2 electrons per orbital. That's a total of 14 electrons. And so if you take a look here, you'll see that the F transition metals are those bottom 2 rows on the periodic table, which we'll actually learn that they go in the middle there. But anyways, if you'll see, there's 14 columns because there's a total of 14 electrons that can go in the F block. And those are the types of orbitals. Now the electrons on the outermost energy level are called the valence electrons, and they're very important in determining how certain elements behave. And so it's the valence electrons that are mostly involved in chemical reactions. And again, we can predict how they will react based off of the number of valence electrons, and we'll learn about that later. Now, the group number, which is the column, will help you determine how many valence electrons an element has, or an atom. And so you'll see that the first column there has 1 valence electrons, the second will have 2 valence electrons. Now, the transition metals, which are those middle ones there, we're going to learn don't contribute to the valence electrons. We're going to learn that later. But if you go all the way to B, which is boron, it's the 5th element on the periodic table, that's the 3rd column. Those will have 3 valence electrons. The carbon column will have 4 valence electrons. Nitrogen will have 5, oxygen 6, fluorine 7, and then that last column will have 8 valence electrons. And we'll talk about that more later. And that's when it comes to orbitals, what I will say is I know that this is complicated and that there's a lot going on here, but what's going to end up happening is we're going to do a lot of practice problems, and as we practice this, it's going to start coming together a lot. So just stick with it and review your notes a little bit. Again, there's really 4 types of orbitals. We have s orbitals, p orbitals, d orbitals, and f orbitals. And just remember the different blocks. So we have the s block, the p block, the d block, and the f block. So those 4 blocks. And that's it. I hope you guys have a great day.